Good morning. This is Lecture 7 in Elements of Hydrology, and this is the last of the lectures that deal with fluid mechanics. And in this lecture, we're going to derive Poiseuille's equation, which helps us assess the velocity profile of water in a pipe. And in the end, we come up with an equation that allows us to calculate discharge in a pipe given a pressure gradient and given an elevation change and given a specific type of fluid that is moving through there that has viscosity. The difference between this derivation and the previous derivation where we looked at the cubic law is now we're going to take a system where before we assessed a two-dimensional profile, a parabolic profile of fluid in a crack between two planes, and then projected that vertically over the length of that crack. We're now going to assess a three-dimensional paraboloid-shaped velocity profile over the length of a tube. And that gives us a different kind of look to our end equation because now we're dealing in a cylindrical type system as opposed to a Cartesian grid. And so that gives us a bit of a different take on our results. So as with all of these, we will start with our image, our diagram that helps us understand the problem. So we'll picture the problem, and then in that picture we'll label everything that we know and then talk about what we're trying to find as a result of this. So let's get started. So on this picture we're going to start as we do with all of them, and that is with a datum. And above this datum we have a pipe. That pipe is inclined to that datum at some angle theta. That will become important soon, as we'll see. Moving through that pipe is water that comes out with some discharge. That discharge is, of course, what we're ultimately trying to determine. The pipe has some length S, and that pipe also has some cross-sectional area A. So now in order to look at this problem and look at more detail on how we're going to derive a solution to this problem, we're going to picture a small element of that pipe inside of there. And that small element of a pipe has some volume dV, so some little part of the total volume dV. So what we'll do now is we will zoom in on that small volume element of the system, and we'll begin to label what forces are acting on that control volume. So let's take dV and let's expand it out. So we have this small volume element that has a control volume dV. It must have some cross-sectional area, and that cross-sectional area has a radius little r. If the cross-sectional area of the control volume is a radius of little r, then we can go back and we can look at what the area is pi little r squared. And then if we go back to our full volume of that pipe, big area A is equal to pi big R squared. So the difference between big R and little r are going to be important in our derivation as we move forward. So we have this control volume dV. It has a radius little r. It has a length ds, which is some little piece of the total length s. It is also at that same angle theta to the datum. And if we look at this control volume, notice that it is changing some distance with respect to that datum over the length of ds. And that change in the elevation, if you will, of that control volume from one end to the other end over ds is a change in elevation of dz, such that the sine of theta, which is the angle that this pipe is inclined to the datum, is equal to the opposite over the adjacent, or dz over ds. So those are some things that we know about the geometry of the problem. Now let's assess the forces that are acting upon this, and first we'll look at the driving forces. So let's go back to driving forces. So the driving forces of this problem are given by some pressure gradient that is acting on this, and that pressure gradient across ds is dp over ds. That is the pressure that is acting from one end to the other, the pressure gradient on that control volume. And so if we pick a centroid to that control volume, then we can assess the pressure that is acting on each side of this. And that is 1/2 of the distance away from the centroid in either direction, such that the driving forces going forward are related to the pressure here, which is P minus 1/2 of the total change in pressure over the distance times that distance times dA. That is the force. So pressure times area gives us force. So we have 1/2 of the change in the pressure going back the other direction, and up here we have a similar setup where we have P plus 1/2 dP ds ds dA, because now we're going in a positive direction in our coordinates, and we're adding 1/2 of the total change in pressure across that distance and multiplying that by the area, which gives us the driving force. The other force that's acting on this system is the one that is due to gravity, and that is what is pulling this down, which is rho g dV. So let me put dP ds here as the pressure gradient. So the gravitational force now is rho g dV. So that gravitational force then is acting, has components that are acting in the ds direction. In other words, it is the component of the gravitational force that is pulling the fluid back down the tube. And so assessing that, we have that if, in our geometry of this problem, if this is rho g dV, then this component of the force acting down the pipe is rho g dV sine of theta. So those are our driving forces, and in order to solve this problem, we have to relate the driving forces to those that are frictional forces. So we'll start now by adding up the driving forces, and then we'll take away from that the frictional force. So on the driving force side, we can basically add up all the parts that we wrote out here, which is P minus 1/2 dP ds ds dA minus dP plus 1/2 dP ds dA minus rho g dV. And because sine of theta we defined as ds over dz, we can substitute that in. dz over ds, and that is equal to our driving forces. Now we can simplify this part down pretty quickly because p minus p goes away, and minus a half minus another half becomes a whole, so that we have dP over ds ds dA minus rho g dV dz ds equals the driving forces. The ds times dA is the volume of this control volume, so that what we actually have here is dV. And so dV is in both of these parts, so we can pull it out. And when we pull it out, what we end up with is dP ds dV minus rho g dV dz ds equals the driving forces. A couple more algebraic steps here. We can take dV out of both of these and move it out. We're also going to divide this by, we're going to pull rho g out of this system, and so we'll have to divide this one by rho g. So what we end up with, and I'll write it up here because this is sort of the one part of our construct for the forces, and these are the driving forces, is we end up with minus rho g times 1 over rho g dP over ds plus dz over ds times dV, and that is equal to our driving forces. So let me make a point here at this juncture and illustrate to you that what is inside of this parentheses is actually something that we've seen several times before. Namely, what we're looking at here in the parentheses is the change in elevation over the distance, which is a change in the elevation head of that pipe. And then we're looking at the change in pressure over that distance divided by rho g, which is effectively the pressure head in the system. So the driving forces in this system are the hydraulic head. Which, when you think about it, makes complete sense, because that's what's driving the fluid through the pipe. If there is no hydraulic head on this pipe, then no water will be coming out the end of that pipe. And so the hydraulic head is effectively our driving force, and that driving force is related to that hydraulic head through the control volume and the type of fluid that's moving through there. So now let's take a look at the next step of this, which is the frictional forces. So now the frictional forces are, we're going to, let's do the frictional forces over here. So the frictional forces. Let's draw that control volume again here. So this control volume, dV, as a reminder, it has a distance of ds, it has a small radius of r, and we can calculate what the surface area is of this control volume, right? It is a cylinder, and that cylinder has a control volume, or that cylinder has a surface area, and that surface area is defined by the perimeter of that, which is 2 pi little r. So that's the perimeter of that circle, the circumference of that circle, times the length of that control volume. So that is our surface area. That surface area is a little part of the total surface area of that entire pipe. Acting on the surface area of this control volume is frictional forces. So if we go back and we look at the problem, remember that in order to assess the amount of water that's coming through there, certainly the hydraulic head is what's driving it forward. But what's slowing it down and what's causing that pressure differential is the fact that there's frictional forces acting on that water, and the frictional forces are acting primarily on the boundaries of that pipe. So we have a stress, and that shear stress acts in a negative coordinate direction, right? It's going backwards. So we have tau that we used as our shear stress variable, and we use this same construct in the cubic law derivation, where we talked about Newton's law of fluids. So in this control volume, the shear stress is acting on the boundary of that control volume, and so the shear stress is related to the amount of that, the frictional force is related to the shear stress times that surface area. So the total shear stress, this total frictional force, is the shear stress times that control area, so that our total frictional forces, if we want to call them our frictional force up here, is tau dAs is equal to 2 pi r tau ds, right? So tau times d, the surface area, is equal to the surface area, 2 pi r ds times tau. So that's our frictional force. So now, in order to solve this, we have to balance the forces. Now, by balancing the forces, it doesn't mean that there is zero change here. This is a system in which there is water flowing, but it's in equilibrium, so the forces are balanced in that system. If it were an imbalanced system, we would be in a transient case in which the discharge would change through time. But we're not doing that. We are in a system where we have constant flow with each point in time. It's in equilibrium. So what we will do now is we will sum our forces. So I'm going to erase this part that we've done so far, because now we have our definitions of our driving force and our frictional force. So now we're going to sum the forces so that the sum of all forces must equal 0. So adding these two forces, we have on the driving side minus rho g dz ds plus 1 over rho g dp ds, which is our hydraulic head, times dV. Our frictional forces, so we add up our frictional force, which we defined as 2 pi r tau ds, and the sum of those must equal 0. So going back to our definition of our control volume is equal to pi r little r squared times ds. Why is that? Because it is the cross-sectional area of our control volume times the length of that. That is the volume of that control cylinder. So now we can take where we have dV, we can replace that information in with what it means in terms of pi and in terms of the radius of that control volume. So our next step becomes minus pi little r squared rho g times dz ds plus 1 over rho g dp ds times ds plus 2 pi r tau ds equals 0. So what we will do next is we solve for tau, because ultimately we're trying to define what that shear stress is so that we can relate that to Newton's law of fluids. So if we solve for this, first thing we have to do is we move this part of the equation to the other side, and then we divide through by all of these parameters. So we will write that out. The first step being 2 pi r tau ds is equal to pi r squared rho g times dz ds plus 1 over rho g dp ds times ds. Ds's cancel. One of the r's cancel. Pi cancels, so that what we have is that our shear stress, I'll write it over here so we can go back and erase these again. Our shear stress we can define as tau equals rho g over 2 times our hydraulic head, dz ds plus 1 over rho g dp ds. And so that is our shear stress. So let's go back and for the moment, let's summarize where we are, because this is an important point in the derivation where we change topics, right? So up to this point, what we have done is we have drawn our problem, we have assessed the geometry of the problem, we have defined a control volume and all the geometric parameters of that, and then we said if there's a change in pressure across that and a change in elevation across that, then how do I sum up those forces to find out what the driving force is, what the frictional force is, and then by equating those two, that the sum of the forces must equal to 0, then I solve what the shear stress on that control volume must be. And notice that the shear stress is related to the type of fluid, or the density of the fluid that we have, so the type of fluid. It's related to the force due to gravity on the system, and it's related to the hydraulic head. So, and I left out, I am apologetic there, I left out one thing in that, And that is that there should be an R there at the end, of course. And that R, of course, is very valuable because that's the size of our control volume that we're dealing with. So, type of fluid, hydraulic head, size of pipe. Those are what control the shear stress on our system. So now that we've solved for forces, we're going to combine this with our knowledge of Newton's law of fluids, and then we're going to solve what must be happening in terms of the velocity profile, and then next the discharge. So let's recall from Newton's law of fluids that the shear stress is equal to the viscosity of the fluid times the cross profile of velocity. Now, in this case, this looks just a little bit different than we did with the cubic law, because now we are assessing the velocity in the s direction. So the velocity in the s direction as it relates to distance away from the centroid or the wall of that pipe. So that's why it is in terms of r, not in terms of x, because the last time x was just a coordinate which was distance from one plane to the other plane in the crack. Now we have a cylinder, and because it's a cylinder, that the only direction that matters is with respect to the center of this. So r being the radius of that pipe. So that is our construct of Newton's law of fluids. So now we can take what we have derived in terms of shear stress and put that into Newton's law of fluids, so that we have the viscosity times the change in velocity in the s direction over the change in the position of that we are with respect to radius is equal to rho g over 2 times dz ds plus 1 over rho g dp ds times little r. So now we get to a point where we have a differential equation. On the left side, we're assessing the change in velocity in the s direction as it relates to the cross profile of the cylinder. On the right side of the equation, we have our frictional force as it relates to our shear stress, I should say, as it relates to the type of fluid, the hydraulic head, and the size of the pipe. So I can separate my variables now, which is the next step that I do, where I have r on this side and I have r on this side, so I want to take and combine the r's all on one side. So that and I'll take the mu over to the other side, so that what I have is the change in velocity in the s direction on one side. Now, and on the other side, I have rho g over 2 mu times dz ds plus 1 over rho g dp ds times r dr. So r dr. This sets up an equation now that I can integrate, that I can sum up all the little pieces of change on each side. So on the left-hand side, I'm summing up all the little pieces in change in velocity in the s direction, and on the right side, I'm summing up all the little pieces of change that is happening incrementally as we move along the radius of that pipe. So the next step is to integrate that. So on the left-hand side, I'm integrating the little pieces in change in velocity. And on the right-hand side, I'm integrating up everything else. But notice, going back to this, the density is constant, gravity is constant, viscosity is constant. This part in the middle here has nothing to do with radius, so it is effectively a constant when we're talking about radius. So the only thing that's not constant is r dr in this particular integration. So I have rho g over 2 mu times dz ds plus 1 over rho g dp ds. Those are all constant in terms of this integration, so that the only thing we're really integrating here is r dr. This is not a definite integral because I have not defined my limits on this. This is going to be an indefinite integral, which means that as I integrate this up, I'm going to have a constant of integration that goes with it. So this is a very simple integration. On this side, we have du sub s, I have the velocity profile of u in the s direction because I've summed up all the little pieces. On the right-hand side, all the constants are exactly what they are. They're still constants, so that is rho g over 2 mu times dz ds plus 1 over rho g dp ds. And then integrating r dr becomes 1/2 r squared, 1/2 r squared as the integrating it up, and that we could add a constant of integration to that result. So of course I can take that 1/2 and I can move it over here, right? So let me just take that 1/2 away. And rather than rewriting it all again, I'm just going to take that 1/2 away, and I'm going to move it over here, and that becomes rho g over 4 mu. So, in order to evaluate this constant of integration, I have to look at what my problem is. So, in this problem, if I take and I look at the velocity profile, I already kind of mentioned at the beginning of this that effectively what we're going to create, because we know this is the case mentally, is that the fastest velocity is going to be in the middle of the pipe. And then if we define the edges to have the frictional force, the resistive forces, if we assume that there are no slip conditions, that no slip condition means that the velocity on the edge of that pipe is equal to 0. At exactly the edge of that pipe is equal to 0. That should create a paraboloid. And so the way to write that boundary condition is that the velocity in the s direction at little r equals big R is equal to the velocity in the s direction at little r equals big R is equal to 0. So the velocity in the s direction at the little r that I'm considering in my control volume scaled up to the total volume of the pipe is equal to 0. So we go in and we place that in. All right. So for the velocity equals 0 when little r becomes big R, so that rho g over 4 mu dz ds plus 1 over rho g dp ds times big R squared plus C1. So effectively that C1 equals negative of all of this. So I could put that back in for C1. See that again? So C1 is here, 0's on this side, so I take all of this and I can move it to the other side of the equation, and it puts a negative in front of it, which means that C1 must equal all of this. If C1 equals all of this, then C1 here in this equation can be replaced by negative all of that. So the velocity profile then becomes rho g over 4 mu dz ds plus 1 over rho g dp ds times little r squared minus rho g over 4 mu dz ds plus 1 over rho g dp ds times big R squared. And that's it. I mean, that's it. Now, we can take and collapse this down quite a bit because all of this is the same as all of this, so that if we write it out in a final form, let me go back and I'm going to take and I'm going to erase these steps now. And I'm going to go all the way back to here. And I'm going to write what my final velocity profile is. I'm going to write what my final velocity profile is on that side, simplified down to the velocity profile in the s direction is equal to rho g, we're going to say minus rho g over 4 mu dz ds plus 1 over rho g dp ds times, because I switched the negative sign here, big R squared minus little r squared. So that's the velocity profile of this system between the control volume and the total volume of the pipe. So if I want to find what the maximum velocity is, the maximum velocity of this pipe is going to be where little r equals 0. So in other words, it's going to be in the center of the pipe. So at the axis of the cylindrical coordinates. So right at the axis of this, or in other words, at little r equals 0, that's going to be the maximum velocity, so that the maximum velocity would be this equation where little r here goes to 0. So that would be the maximum velocity in the center. And the velocity at any point in that pipe is related to the size of that pipe and the position in there that I'm making my measurement. If I look at this special case of horizontal flow, this is where now I'm going to calculate a discharge. So let's go back and let's erase this. And let's look at horizontal flow, because what we'll do now is we'll assess what happens in a system where all we really have are the driving forces that are related to the pressure gradient, not driving forces that are related to change in elevation head. So pressure head, but not elevation head. So in a system where the pipe is horizontal, here are the following conditions. Theta equals 0. There is no change in elevation, which means that dz ds is equal to 0. But now, there is a ds. It's not that ds is equal to 0. It's that dz over ds is equal to 0. What this must mean is that ds is equal to the change along the x-coordinate system. It's not related to any change in the z-coordinate system. So dz becomes equal to ds, or dx. And dz is then the one that must equal 0 in order for theta to equal 0 in that horizontal condition. The other thing is that, of course, we know that discharge is equal to the velocity times the area. So that the little piece of discharge that we have, dq, is equal to the velocity times the little piece of volume. So what we have to do in order to solve what the discharge is in this pipe, let me go ahead and I'm going to erase this now that we've got a velocity profile solved, is we need to draw a second diagram that helps us understand what this looks like. So in this diagram, we're going to look at our little control volume, and we have our larger cylinder. So the little control volume had a radius of little r. The entire pipe had a radius of big R. This pipe has a circumference of 2 pi r. And we have area here. If we want to sum up all of the little pieces of area, realize that what we have is we have a set of rings. And in these rings, we have little pieces of the total radius, and we have little pieces of the total cross-sectional area. All of those are relevant here. Sorry, that's not symmetrical. Let me draw it now the other way, which is looking at it from the side. So that really what I'm assessing here, when I'm adding this up, it's almost like a nested structure of little pieces of the total, right? So I'm going to be looking at each of these little cylindrical slices of the total, almost like a child's toy where they nest inside of each other, where I'm going to add up the velocity or the discharge in that little piece, and then each of these subsequent pieces with the velocity of each of these. So u sub x now, because we're considering it in the x direction since it's horizontal, u sub x is increasing as we move towards the center of the pipe. So, in this geometry, the little piece of area is equal to 2 pi little r times dr. So 2 pi r, of course, is the circumference of the circle at that r. Dr is the little piece of change, and the total cross-sectional area is the sum of that circumference times the little piece of change in area across that width. So now we can take that definition of dA and we can put it in here for our discharge, such that dq is equal to the velocity profile, I should put in the x direction because that's the way we're looking at this, times 2 pi little r dr. So that gets us a definition of dq. Let me go back over here and write my conditions for the horizontal flow. dz must equal 0 and ds must equal dx. So we can combine this equation that we have here with this equation that we have here. We can do that because we have a relationship that dq was equal to u dA, right? And here is our u, and there's our dA. So now we can write this out as dq equals minus pi over 2 mu dp dx times big R squared minus little r squared times r dr. How did I get to there? Well, number one, I was able to say 2 pi r here, and 2 pi r cancels that down and leaves pi over 2 mu as the result. In terms of why this just collapsed to dp dx, well, if I go back and I look at this system, that takes dz ds goes to 0 in horizontal flow. That leaves 1 over rho g dp ds, and the rho g can come out and cancel that rho g there, which means that it's no longer outside the parentheses. So this is what the little piece of discharge is. So now in order to get the total discharge, I have to go and sum this all up. So I get dq, and I'm integrating from 0 now to the total discharge. I'm making this a definite integral. And so because it's a definite integral, I won't have a constant of integration at the end of this. Pi over 2 mu, those are all constant. dp over dx, that is a constant. Now I'm integrating from 0 all the way to big R, because that is the total diameter or total radius of this tube. R squared minus big R squared minus little r squared times r dr. So I can do this as a piecewise integration where I integrate each step. So r dr multiplied by this, r dr multiplied by this, and then I can integrate both of those sides. So I'm going to not write all of this stuff out here because that remains the same. But here I have an integration from 0 to big R of capital R squared r dr. And then that is minus integrating from 0 to big R of r cubed dr. So I can integrate those up. Big R is constant in this, remember? Even though we are finding out what the total impact is, what the total discharge is across big R is a constant. So really all we're integrating here is little r. So we have big R squared, little r squared over 2, evaluated from 0 to big R. And then I have over here minus r to the 4th over 4, evaluated from 0 to big R. When I collapse this down after I evaluate this, of course, if I put 0 in for little r, that goes to 0. If I put 0 in for little r, that goes to 0. So that in the end, I have big R squared here, so that goes big R to the 4th there, and big R to the 4th there. Right? So what I have when I do that is I have Q now, because I've summed up the whole discharge, is equal to minus pi over 2 mu dp dx, those are the constants that I had, times big R to the 4th over 2 minus big R to the 4th over 4. And in order to make constant the denominators the same, what I need to have is the following. That the discharge is equal to minus pi over 8 mu times dp dx times r to the 4th. And that is the discharge in the pipe. So that is effectively Poiseuille's equation. So by having a pipe, now the discharge is related to the radius of that pipe to the 4th power. In the cubic law, when we derived that, we saw that the discharge was related to the cube of the width of the pipe, or the width of the crack. So now we have to the 4th power. This was done in horizontal flow. we can, through a similar type of derivation, illustrate that it is a similar result, but that result in place of here has the hydraulic head, and then we have rho g out here. But that's a little bit of a longer derivation, but I wanted to show you the horizontal system. So this is Poiseuille's equation. We got to this through a few things. One is we drew our problem like we always do. We assess the geometry of that problem. Once we assess the geometry of the problem, then we look at a control piece of that and we assess all the little changes that are happening on that. Then we assess the forces that are acting on that control piece, and we sum up all the driving forces that are moving the water forward, which are related to pressure and related to change in elevation. And then we're looking at the forces that are resisting that flow, which are effectively friction, and that friction is related to shear stress. So then we equate those forces together to get the forces balanced and to sum up those forces. And what we end up with is an equation that we can use then to derive the velocity cross profile. That velocity cross profile is exactly what we expect, and that being that it's fastest in the middle of the pipe, and it's shaped like a paraboloid, where in our system we have a no-slip condition where there's no flow on the circumference of that pipe, because that's where the shear stress is being applied. So then we come up with a velocity cross profile where we can calculate what the velocity is at any point in that pipe, measured from the center moving out. Then through, again, assessing the geometry and what the cross-sectional area means in terms of that velocity cross profile, and then what discharge must be in terms of that velocity cross profile, we can then sum up all the little pieces in discharge because we know what our velocity cross profile must be. We sum all that up, we integrate it up, and we find out that it's related to the fourth power of the radius of that pipe, and that is Poiseuille's equation. So this lecture takes us effectively to the end of this sequence on fluid mechanics. Now that we know this, we can go back and we look at natural systems and help us understand things such as where is the fastest velocity in a stream? What happens in terms of discharge as the velocity goes up? Where do you see the changes in discharge? Where should you measure the maximum velocity in a system? What does that mean in terms of the boundary conditions of a stream? And how does that mean that the stream evolves through time? It's not a direct correlation because this was in ideal conditions with no slip conditions and smooth boundaries and all of those things. We know that's not the case in nature, but at least this gives us a framework to build upon. And now what we'll do is we'll take this back, like I said, to natural systems. We can use it in stream channels. We can use it in cave systems. We can use it in any case in which we have a flow, free flow moving through. It can be open channel, which means it's free to air, or it can be pipe flow in which it's enclosed inside of a cylindrical type pipe. In all cases, that really helps us understand a bit about the mechanics and how water moves. And we can even take this, and if we really want to look at it at a more microscopic level, we can understand then that inside of, like, let's say a sandstone aquifer, there are stream tubes in between all of the grains that connect the pore spaces, and those stream tubes, in a theoretical construct, behave similar to Poiseuille's equation, and using Poiseuille's equation in that kind of stream tube setting and adding up thousands and millions of these possible stream tubes, what we arrive at that way is Darcy's law, as we would hope to find. So that concludes this lecture on fluid mechanics, and we'll move into understanding stream channels and sediment dynamics next. Thank you.